The Electronics and Communication Workshop and Practices presents the working of the MCB, presented by Zil Vandra, Prisha Bhatt, Mehak Ranka. The visual credit of the videos goes to the YouTube channel
Lasix.
A tiny interesting device called MCB protects you and your house from electrical mishaps. This breaker saves you from two situations. First, short circuit, and second, overload conditions. In short circuit scenario, the MCB trips in less than 3 milliseconds and isolates the internal connections. Let's see how this smart device detects current chaos so quickly and precisely. A simple device called fuse, which has low melting point wire, was used for home protection in earlier days. In both the fault condition mentioned previously, the current spikes up, resulting overheating and fusing the wire or breaking the circuit. However, every time the fuse would blow, you have to manually replace it. Until you can do, good luck with the blackout. This is the most commonly occurring situation, is why circuit breakers were invented. The circuit breaker is an automatic on and off mechanism that keeps one side of the wire moving and another fixed. During an electric fault in a circuit opens wide, we are done with the MCB design. After that fault ends, simply manually turn it on. Before getting more into MCB design, a small note about the current directions. An MCB gets activated in less than 3 milliseconds is way lower than the half cycle period of an AC current, so it is okay to show current flow in a single direction throughout the analysis.
Now the question is, how does the system recognize the occurrence of an electric fault? The answer is that it has sensing elements which activates a triggering mechanism. Let's first see how we can design a super quick triggering mechanism, which opens a wider clever mechanism to achieve this objective is shown here. This mechanism has a lever to which a rectangular ring is connected as shown. The rectangular ring is connected by two springs and a central lever. In this position, both the springs are in a neutral state. When the lever moves up, the bottom springs compress and the top spring expand. The force of both springs are eventually transferred to the lever via the rectangular ring, and the force will be in the upper direction. As you can see, the rectangular ring is initially at a negative offset to the center of the lever. The torque produced by the force acting on the rectangular ring will be in the clockwise direction. If you release the lever in this position, this clockwise torque will bring the lever back to its initial position. However, if you push the lever further up, you notice anything peculiar about this distance, it suddenly becomes positive, which means that after a critical limit, the torque will act on it in a counterclockwise direction. When the MCB is on, this will be the position of the lever. The structure of the MCB will block the lever from rotating further counterclockwise. Now, if external trigger turns the lever slightly, the torque on the lever suddenly becomes clockwise and the circuit opens wide quickly without the need of an external force.
As the operator pushes the lever down, you can see in ultra slow motion how the mechanism operates in practice. Now we'll see how the input trigger is generated when the fault occurs. This is done with the help of an electromagnet. It produces magnetic fields proportional in nature to the current passing through them. Then, as the current increases, the magnetic field increases. The current rises 1,000 times in milliseconds. This results in a very strong magnetic field. An iron cylinder and pin is placed inside the electromagnet on a spring. The strong magnetic field pulls the cylinder downward, thus pushing the pin. This tiny movement of the pin is the input trigger, which leads to the opening of the circuit. This doesn't happen while normal current flow because the pull to the cylinder cannot overcome the spring tension, while the short circuit current is 10 or 1000 times the normal current. As soon as the contacts are opened, the current doesn't just stop flowing. Since the short circuit current, the fault current is of very high value, this leads to air discharge. To extinguish the arc, a component called arc runner or arc chute is used. An arc chute is made up of parallel plates arranged at small intervals. The arc current leads to a huge temperature rise. This temperature rise can cause heavy damage, needing the arc to be killed. Now resistance increases length and decreases when increase in area. We need increased resistance, which is why the contact point is kept high after the circuit opens. Since the air is hot, the arc will be pushed up. Later, the arc is divided into small chunks, thus reducing its area. With increased resistance, the arc dies away at current zero.
A tiny